So from last time, we saw that a representation of the easiest semigroup you can imagine, basically the natural numbers, is just uniquely determined by its value at the generator 1. Okay, not surprising. And it doesn't really need to live to a unitary representation of the integers. And let me just explain what do I mean by that. And so one typical example of an isometry is called a unilateral shift. So what you do is that you take the L2 space of the integers. You think about the L2 is basically, because n here is discrete, so you take a bunch of orthonormal bases, so we call them En, and here n is inside the natural numbers, and then you take their L2, like basically you take their closure. Okay, so that's a L2 space. And the unilateral shift is that you shift all the basic vector to the right. Okay, so this operator, you should have seen it in function analysis a lot, and give you a lot of counter examples when you talk about the weak operator conversion and so on. But anyways, this operator, you can see that it maps an orthonormal basis to an orthonormal basis, so it has to be an isometry. So as is an isometry, but as it's not a unitary, because well, nothing will get mapped to the E0. Okay, so E0 is kind of missed in its range. Okay, the range projection is basically spanned by all the En, where n is at least 1. Okay, greater than or equal to 1. It will miss a little space. All right, so this is not a unitary. Okay, so not unitary. And this is basically what happens, basically a typical example of a shift of a pure isometry that's not a unitary. And there is, in fact, a very nice theorem in operator theory that tells you all the isometries can be decomposed as a shift part and a unitary part. Okay, so if you take an A10, you probably will see this proof. This is called the Wold decomposition. All right, so this is a really nice theorem. Wold, just a little word on this. Wold, actually, when he first studied this, he was studying some stochastic process. And in reality, if you take any statistic course like forecasting, there's actually a Wold decomposition of those stochastic processes as well. It decomposes a certain time series into some static part and some shift part. So any case, this is related. Okay, so your original motivation comes from these probability and statistics, and later on, but Norman realized, well, this is just a theorem talking about the operator as well. So that's the Wold decomposition we have. Okay, so this is really due to von Neumann at least. All right, so what it says is basically the following. So if you take any V isometry inside some B of H, okay, then what you can do is that you can decompose your H as, so H can be decomposed as one part, let's say H1 plus H2. And your V is going to be decomposed as a shift, maybe some multiple of them. Okay, you can have a direct product, direct sum of these shifts, maybe alpha copy of them for some cardinal alpha. And then you have these direct sum, a copy of a unitary. Okay, so here the S alpha is basically alpha copies of the unilateral shift, and that's actually an operator on the H1 part, and the U is just a unitary operator on the H2 part. Okay, so every isometry will decompose this way. Okay, so in terms of representation of the semigroup, this is essentially just saying a representation of the natural number. In other words, a representation of this single using this single isometry. It decomposes as a part which is given by the unilateral shift, and another part is the unitary, basically a representation of the group. Okay. All right, so let's briefly. I will just want to briefly outline the proof because it's quite beautiful, and I will leave some details. So if you are going to take A10, this is going to be explained in much more detail. It's related to these two-plus algebra and so on. So I'm not going to give you a full introduction, but the idea is that how you build the space is the following. So you let first of all you let W to be the kernel of the V star. Okay, another way of writing it is you consider its range projection and you see what's missing. Okay, so you apply that to your original space, you call it H, and you apply that range projection, you see what's missing, what's not in its range. Of course, basically it's the identity minus that. So that's a projection onto a space, and you let that space to be W. Okay, so this is a subspace inside H. And first of all, let's consider one thing. So if you have any n not equals to n, okay, let's say n is strictly less than n, okay, some two natural numbers, and if you take any h and k in from this W, so if you consider what happens when you try to say Vn times h and you have a Vn times k, okay, you want to apply this inner product. Well, because one is greater than the others, for example, here m is bigger, so you can move the m to the left-hand side. So you say, well, that's all the m become V star on the left, and we have a Vn, and then have a h and k. And because V is an isometry, so the star on the left will cancel out the V on the right, okay? The M copy basically now you can pull out the N copy, then cancel out the V to the N, and you end up with the V star of N minus N, okay? The number doesn't really matter. The point is there is some V star, and because the H is inside W, well, W is the kernel of the V star. So the V star, only one copy of V star will kill off this H. This part will have to be equal to 0, okay, because n minus n is greater than 0. And of course, as you can see, if n is greater, then you just move the n to the other side, okay, same proof. But in any case, this is equal to 0. So this essentially what it proves is that if you let, let's say, Wn to be the range, okay, you apply Vn to the space W, then what you get is that these collection of spaces Wn and going from 0 to infinity, okay, for every n inside the integer, natural number, they're pairwise orthogonal to each other, okay, so they're pairwise orthogonal. And because they're pairwise orthogonal, if you just consider what happened, let's say H1 to be equals to, you take their direct sum, okay, of these Wn and greater than or equal to 0, okay, that's going to be a subspace of H. And if you think about what happens when you apply V to this space, okay, so first of all, this H will have to be invariant under V, all right, so because V of each of these Wn is going to be contained in the W of n plus 1. Okay, and you take the direct sum, so that just means V of these H1 is going to contain in H1. Okay, so H1 is invariant. And it's also co-invariant. So if you take a V star, okay, if you want to move it backward, I give you a W of n plus 1, then it will move back into these Wn. And the V star of the first one, the W0, basically W, is in the kernel, so V star will kill it off, okay, so that's equal to 0. But in any case, these two will tell you if you apply V star to something in H1, that's also landing inside H1, okay, either inside some Wn, okay, you reduce the level by 1 or you map it to 0. But in any case, this H1 will reduce the V, okay, so the point is H1 reduces V. So in other words, V, if you write it as an operator matrix, it will look like something here that's from H1 to H1, but these two entries will be 0, okay, and you let that to be the H2 copy, and that's where it is. So the claim is the following. So essentially, to prove this, the wall decomposition, you just need to look at what's this component in H1. The claim is that if you restrict to H1, then it's isomorphic to a bunch of copies of unilateral shift. And moreover, you can actually describe how many they are. It's actually just related to the dimension of this kernel, okay, this W. And if you restrict to the H2 space, and because think about it, the idea is that all the thing that's not inside the range of V is already captured as a subspace denoted by this W. In other words, it's inside H1 already. So inside the H2, there's everything is inside the range. So this is going to be a unitary. Okay, so that's where you get the unitary part, right? So if you want to check, well, the second part is actually quite easy. So let's just check the first one. So the idea is that for every, so E1 up to, let's say, maybe say E lambda is an orthonormal basis of your W. Okay, your W is a subspace, maybe infinite, but for each of these orthonormal vector of your W, it kind of generate a copy of the S by the following. So if you just consider, let's say, H1 lambda to be the direct sum, or let me just write it as a direct sum for now, and you basically take all the V to the power n of a vector E lambda. Okay, this is just no other than the span of all the V and E lambda. Okay, n is greater than or equal to 0. All of these, and you, of course, you close it up. Okay, so they are going to be pairwise orthogonal to each other as well. And if you think about what happens to the V when you restrict to this H lambda, H1 lambda, then this is going to be unitarily equivalent to the S. Okay, so it shift the vector Vn E lambda to Vn plus 1 E lambda. Okay. So it's really just a unilateral shift on this part. And because they are orthogonal to each other, your V just decompose as a bunch of unilateral shift. And how many of such a copy is depending on the dimension of your W. Okay, so in any case, that's just an outline of the proof. And the second one is fairly simple as well. You can just double check. So this finished the proof of the wall decomposition. So in other words, as you can see that for representation of this easiest semigroup, basically the set of natural number, representation decomposed as two parts. One part is just purely happens on the semigroup, basically given by this unilateral shift. Okay, they cannot be inversed. Okay, you cannot extend it to a representation of the integer. The other part is the unitary. So that's the part where you can extend it. You can pretend it's basically a restriction of a unitary representation of the integer. You restrict it to only the positive part. Okay. So as a corollary of the wall decomposition, you actually have a very nice theorem. This is called the Colburn's theorem. Okay. This essentially tells you the following. So if you take any V, if it's a proper isometry, so by proper, I mean if you have a VV star that's not equals to the identity. Okay, if it's equal to the identity, then of course it's a unitary. Okay, so proper just means it's a non-unitary isometry. All right. And then if you can, well, because V is inside some B of H, you can think about it's a C-star algebra, basically the C-star algebra generated by V. Okay, you take all the V stars and you take all the V's and you compose them, you build an algebra, you close it up in the norm, you get a C-star algebra. That C-star algebra is going to be isometrically isomorphic to the C-star algebra generated by the unilateral shift. Okay, so this is C-star of S. And what's the nice thing about this theorem is the following. So the idea, well, I'm not going to prove this theorem. This is just a quite easy consequence once you have some description of what's the C-star of S, and essentially the C-star of unitary will be basically a quotient of the two-place algebra by the set of compact. And you can see that basically the shift part will give you the norm on the C-star of V, and the C-star of U part, the unitary part, will be a quotient, so it's always less than the shift part. That's why the shift part is kind of universal, and that's give you this isomorphism. But the idea is the following. So if you look closely enough to the C-star of S, okay, so S is just this unilateral shift is just really the left regular representation. Okay, so remember, for group, you have a left regular representation of your group. Basically, you represented on the L2 space of your group G. But the unilateral shift is just a left regular representation of your semigroup. Okay, so you take your semigroup, you build an L2 space, you define the left shift, and from that way you can build a C-star algebra. This is for the group case, you got a reduced one. So we can build the same thing for at least for the semigroup N as well. Okay, so let me just write down the definition here. So if you P is a semigroup, by a semigroup I also means unital embedded in the group and so on. So the reduced C-star algebra is essentially generated by the left regular representation. So the left regular representation is basically lambda from P to B of the L2 of P. So where lambda P of EQ, the EQ is an orthonormal basis, is given by this left shift, so del E of PQ. And the reduced C-star algebra, the reduced, let's call it the semigroup C-star algebra, that's denoted by really similar notation as a C-star lambda of P, is essentially just the C-star algebra generated by all these lambda P, okay, P inside P. All right, so there's really no ambiguity inside for the reduced, how we define the reduced semigroup C-star algebra. You can think about it this way, and it's always sitting inside the B of the L2 of P, okay? That's always the case. So what happens is that the covariance theorem basically tells you the following. If you think about what happens to the universal one is that, well, ideally you want to say, well, the universal C-star algebra will be the one generated by all kinds of isometry. So you take the direct sum of all kinds of isometry. And when you take the direct sum of all kinds of isometry, that's clearly going to be a proper one. And the covariance theorem says, well, that one is going to be equals to your reduced one. Okay, so let me just naively, you'll say the C-star U of this N. Okay, so right now let's just write it this way. So naively, you'll say that's the universal C-star algebra generated by a single isometry V. Okay, so basically you take the direct sum of all the isometry and you do the C-star algebra there. And covariance theorem says the full one or the universal one is isomorphic to the reduced one. Okay, so this is what essentially what the covariance theorem, you can understand it this way. Okay. All right, so that looks nice. Well, but it shouldn't be too surprising. The reason is that from last week we saw that these amenability, whether the full and reduced C-star algebra are the same, is really related to whether the group is amenable or not. And if you think about the set of natural number, well, they're just it's a very easy, probably the easiest semigroup you can think about is a billion. It's generated by a single element and it's embedded inside a set of integers. So if you have some notion of a amenable semigroup, then the set of integers should be the first example of something that's amenable. Okay, so basically, you cannot go any simpler than that. Okay, so you really expect these two to happen. Okay, simply because you expect if there is some notion of amenability, you expect n is to be amenable. All right, of course, then a lot of people say, well, if it happens to the easiest one, well, how about let's try it on the next one? Okay, so let's try it on the N2. Well, the N2, that's basically you can embed it into the very Billian semigroup Z2, okay, just two integers, and it's generated by two things, okay, 1, 0, and 0, 1, basically generated by a pair of commuting isometries. And you can consider the C-star, the reduced C-star algebra of these N2 basically generated by this something called the bi-shift. Okay, so this is the C-star algebra generated by S1 and S2, where S1 and S2 belongs to the L2 space of the N square. S1 of the E of, let's say, NM is the shift in the first coordinate, okay, N plus 1 NM. And S2 of the NM is shift in the second coordinate, okay, N and N plus 1, okay. So there's really no controversy on how you define the reduced one, okay, that's fairly simple, okay. And then you think about what's the universal one, and you're really tempted to do the same, okay. You want to say that's the universal C-star algebra generated by a representation or isometric representation of your n squared. So that's uniquely determined by this value on these two generators, basically 1, 0, and 0, 1. So they have to commute because, well, the n squared is a billion. So I want to say, well, v1, v2 is equal to v2, v1. Okay, so you take the universal one, okay, you can build a universal C-star algebra. Basically, you take their direct sum and you do a C-star algebra like that, and you get a universal one, okay? Well, the idea is that if there's, again, any notion of amenability, then n squared being very abelian and embedded inside C2, having nice generator, you're expecting these two are the same, okay? But they're not actually, okay? So here's just a fact, okay? They're not, okay? So if you define your universal one in this way, it's not isomorphic to the reduced one, okay? There are really many reasons of why this fails. Probably the one reason is that you don't really have a nice wall decomposition. Okay, in fact, if you think about what happens when you have a pair of commuting isometries, okay, well, you can try to decompose it. Okay, you will imagine, well, maybe one will decompose as a unitary and a shift. The other will decompose as a unitary shift, and it will just divide your space into 4 cases. Basically, both are unitary. That's basically a representation of the Z2. You may have a unitary plus a shift. Looks like a representation of the Z times N. And you do a shift and unitary. And the last piece you will imagine, you hope is a bi-shift. Okay, it's just really the left regular representation, and turns out it's false. Okay, so you can there are some representations. So maybe I'll just give you an example. Is that if you just consider you build the L2 space of all the n and m, where n is greater than or equal to 0, or m is greater than or equal to 0. So you think about this is your space. For each of these integers, you have a orthonormal vector. And the two things, your two shifts are basically what you expect them to be. So one is shifting to the right. Okay, so shift to the right. So this is, call it S1. And the other one is shift vertically. So you go up. Okay, so that's basically your S2. And what's the nice thing about, well, nice or bad thing about this representation is that you can see that neither S1 and S2 are unitary or just a pure shift. Okay, the idea is the S1 is unitary on the upper half, but not unitary on the lower half, and S1 is unitary, S2 is unitary on the right hand side, but not the left hand side. So these kind of representation kind of puzzling for a long time, and there are some nice characterization due to Popovici. I recently learned about this. It's really interesting, and if you want to read about it, you can feel free to let me know, and I can give you some reference. But in any case, the idea is that the wall decomposition is really difficult, and you don't have a nice and clean wall decomposition when you have a single isometry. So people start to think, well, does it mean that there's no way to define some kind of amenability, or there's something else? Okay, so well, apparently you want some idea of amenability. So the idea is probably, well, the universal one is wrong. Okay, so really we need to add some extra condition on this on the universal. We cannot just take all the commuting isometries. That will give a C-star algebra that's too big. Okay, so that's the idea. So what is the correct notion of a universal C-star algebra? That's a puzzling question for a long time, until actually our very own Andonika introduced his notion of quasi-lattice ordered and what's now known as the Nika covariant representation. So I'm going to talk about that in the next video.